Hi, in today's lectures, we are going to study the deformation and stresses in members subjected to a new type loading, a torque. To explain, a torque is a moment that tends to twist a member about its longitudinal axis. As you can see, this topic is a primary concern when we design a dry shaft to be used in vehicles or machinery. That being said, let us study a circular shaft whose original shape is shown on the screen. To understand its deformation later on, let us draw a grid of circular and longitudinal lines perpendicular to each other. Imagine that this grid is very dense to the point where we can consider the red area on the surface of the shaft to be a rectangle, a flat rectangle. The following is the elastic deformation of the shaft when a torque is applied. We observe the following from the deformations. First, the longitudinal grid lines tend to distort into a helix and the rectangular red area become a parallelogram. Second, the radial lines on the cross-section of the shaft remain to be straight lines but rotate a certain angle. Now let us analyze these deformations in details so that later on we can base on those to understand the stress distribution within the shaft. For convenience in our visualization and analysis, let us consider the rectangular red element on the surface of vertical shaft on the screen, with the line OO prime being the longitudinal axis. Let us zoom in the element. Now let us see the detailed deformation of the element when a torque is applied. Before we continue, there are some important terminologies that I need to mention. First, the angle phi that you are seeing on the top surface of the shaft is called the angle of twist that we will study in the next lectures. Second, the angle d phi on the top surface of the pie shape is the angle of twist corresponding to the length element dl of the shaft. Now, based on the deformed shape of the red element, we can predict the stress on each of its four sides. If you remember from a previous lectures, this deformation suggests the presence of shear stress only. I believe if you look at the direction of the torque, you will see this makes sense. Now suppose we want to find the magnitude of this shear stress. Let us see how we should proceed. Based on the Hooke's law for shear, we know we can find the shear stress based on the shear strain, which is the angle gamma as follows. As we are also interested in knowing the distribution of shear stress in the entire body of the shaft, let us see what happens to the angle gamma when we move from the boundary to the center of the shaft. As you can see, the shear strain or angle gamma decreased to zero at the center of the shaft. What that means is the shear stress will be zero at the center of the shaft when the distance represented by Greek letter rho is zero and be maximum at the boundary of the shaft when the distance rho is equal to the radius of the shaft. Now let us see the detailed relationship between the distance rho and the shear strain gamma. First, let us provide names for the points on the screen. Then, based on the similar triangles, we have the following. From here, we can see the linear relationship between the distant rho and the shear strain gamma. As you can see in the formula, rho max is equal to c, the radius of the shaft's cross-section. Gamma max is the maximum shear strain which occurs at the boundary of the shaft. Now, with this relationship being known, we will try to develop the formula to determine the shear stress. From the Hooke's law for shear, we can see the linear relationship also between the distant rho and the shear stress tau. So now if we can find the value of the maximum shear stress, we will be able to determine the shear stress at any point on the shaft's cross-section. That is what we will do next. So how can we find the maximum shear stress? To be specific, we are trying to find the maximum shear stress on this cross-section. For that, let us plot the free body diagram and use the method of section to find the internal torque at that cross-section. Back to our question of finding the maximum shear stress, what we know at this point are the following. First, when we go from the center to the boundary of the cross-section, the shear stress increases linearly from zero. Second, if we divide the cross-section into small differential areas, like this dA, then sum of moments caused by the shear forces on this area about the center of the cross-section should be equal to the internal torque. So let us see whether we can use these two pieces of information to find the maximum shear stress. To start, we know the equation to find the force dF acting on area dA. It is equal to the shear stress at that location multiplying with the area dA. Then we can multiply that force with the distant rho to find its moment about the center O. Since this is the moment caused by the shear force on the area dA only, if we integrate this moment over the entire cross-sectional area, the result obtained should be equal to the resultant internal torque at the cross-section. We just mentioned this earlier as the second piece of information. In this equation, you can also see the use of the first piece of information where the shear stress is replaced by the green formula. From here, we can obtain the formula to find the maximum shear stress. For clarification, T is the internal torque at the cross-section. C is the radius, and Z is the so-called polar moment of inertia of the shaft's cross-section. Finally, after finding the maximum shear stress, we can find the shear stress at any point on the cross-section by using the following equation. As you can see, when the distant rho is zero, meaning when the point is located at the center of the cross-section, the shear stress at that point will be zero. Now let us see how to determine the polar moment of inertia for a solid cross-section as the one shown on the screen. To make it simple, let us change the differential area from square to a ring-shaped element. Then it is easy to find the area of this ring for doing the integration. Since the ring is extremely thin, its area can be determined by multiplying its perimeters or circumference with the thickness. As you can see, for a circular shaft with solid cross-section, the polar moment of inertia is equal to pi over 2 times c to the power of 4. In the case where the shaft is hollow, we can follow the same procedure to find the polar moment of inertia of its cross-section. In that case, the polar moment of inertia depends on the inner and outer radius. With the above result, we can now visualize the distribution of shear stress on the cross-section of a shaft for both solid and hollow areas shown on the screen. While this gives us an impression that the shaft tend to fail at the cross-section because of the shear failure, that is not the case for the shaft made of wood, which tend to split along the axial plane. This mode of failure can be explained easily if you recall a very important property of shear stress that we learned before, the so-called complementary property of shear. To be specific, let's say this is the distribution of shear stress on the cross-section. Then if we section through the shaft further, like the following. Based on the property, we will be able to understand the distribution of shear stress on the axial plane. These longitudinal shear stress are those that cause the failure of the wooden shaft, shown on the previous slide. In a similar manner, we can visualize the distribution of shear stress along another radial line of the cross-section. To help you have a much better understanding of the topic, let us visualize the stress on the following volume element. Here will be the result if we zoom in. You can see that the two elements are subjected to pure shear stress. As the red element is at the boundary of the shaft, it is subjected to the maximum shear stress. Now to summarize, we started this lecture with an understanding of the deformation of circular shaft subjected to torsional loading. Then, based on such deformation, we predict the distribution of shear stress on the shaft's cross-section. Specifically, the shear stress has a linear distribution along a radial line, being 0 at the center and maximum at the boundary of the cross-section. Then, given the condition that some of the moment caused by the shear forces on differential area of the cross-section about the center of the cross-section should be equal to the internal torque, we were able to develop an equation for determining the maximum stress. Finally, we concluded the lectures by visualizing the distribution of shear stress on both cross-section and axial plane. I hope what we just discussed are clear and make sense. Let us stop here for now. Thank you and see you in the next lectures.